third part and last part of this lecture 9. And as I promised, now we will see how to undo the Laplace transform calculation, let's say, so the inverse Laplace transform. Just to remind you that we also saw this for the Fourier transform, and as I said previously, that we are going to use these elements, the Fourier transform for partial differential equations and the Laplace transform for ODEs, ordinary differential equation, and the strategy is exactly the same in both cases. We will have an equation, we will transform the equation, so we get a new one that should be easier than the first one, than the original one. Then we solve that second equation, the transform equation, but then we are not really interested in the transformed solution. What we really want is the original solution of the equation, so we need to go back to undo this transformation. And that's why last time we saw, like a couple of lectures ago, how to invert the Fourier transform. And now we are going to see how to invert some Laplace transforms. So that's the idea. So here, do you remember that to solve partial differential equations with Fourier transform, one of the key tools was the fact that given a function, we can Fourier transform it, but then once we have this new function, we can anti-Fourier transform it or inverse Fourier transform this function. So we are going to do the same argument with our Laplace transform, with our new object. So back then, for solving partial differential equation, we Fourier transform the PDE, then solve the easier ODE that we got in terms of this Fourier transform of U in the variable t. And then to find the original solution, we inverse transform this function. Okay, so now we are going to learn about the inverse Laplace transform. So next lecture we can solve some ordinary differential equations. Okay, so again, to be able to solve these ordinary differential equations via Laplace transforms, we need to introduce the inverse Laplace transform. Okay, so for a function g of s with s positive, we say that f of t is the inverse Laplace transform of f if they verify this identity. And we denote this f as the inverse Laplace transform of g of s, with this notation to the power -1. So first difference, notice that here we are not given an explicit formula of how to compute this inverse transform. And we will see with examples how we can solve the functions that are involved in this course, in the exercises that you have to do like on Thursday or in the exam or in assignments. So we are going to see a couple of tools. An explicit formula can be given, but we are not going to give it in this course. So we will focus only in a couple of in certain type of functions, and we will see how to solve them, how to find the inverse Laplace of these special functions. So first difference with Fourier transform, here we do not have an explicit formula. We are just giving the definition that a function is the inverse Laplace transform of the function g if they verify this identity. When I Laplace transform f, I got g. Okay. Then, this is what I said, that in this course we will compute inverse Laplace transform by using known Laplace transforms and the properties that we saw in the second part of the lecture from 1 to 4, that we can briefly mention them. The linearity was the first one, how the Laplace transform acts in derivative of function was the second one. The third one was that the Laplace transform takes powers of t into derivatives of the Laplace transform. And the fourth one was that the exponential function goes into a shift. Okay, for more details, just please read, check the notes of the second part. Okay, we are going to use that the inverse Laplace transform is also linear, so this will be also a key element. If we have a linear combination of functions, then the inverse transform would be just the linear combination of the inverse transform of these functions. Okay, example. Find the inverse Laplace transform of this gs equal to 2/4 plus s minus 1 square. Here we detect that this guy looks quite similar to something that we compute in the second part of the lecture, which is alpha over s squared plus alpha squared, and this was the Laplace transform of the function sine of alpha t. And here our alpha seems to be 2, but there is just a little detail, which is this minus 1. So if this minus 1 wasn't here, then we can say, this is just the Laplace transform of sine of 2t, right? Because here we have a 2 and here we have a 4. But we do have that minus 1. So now you need to remember some property, and we said this minus 1 is a shifting. So which property is related with shifting? The fourth one that relates exponential functions and shifting. So this is what I was saying. This is almost this Laplace transform, but we have this s minus 1 bothering. Now we remember that the Laplace transform takes exponential into shiftings. This property was, we can rewrite the property here. So exponential to the power beta t times a function f goes to the Laplace transform of the function f here, and this shifting s minus beta. So when we take beta equal to 1, we would get here s minus 1. And if we get f equal to sine of 2t, we will get exactly this expression here, which means from what we saw in the second part, and we recall here at the beginning of this exercise, we get exactly our g of s, 2 over s minus 1 squared plus 4. So a function is called the inverse Laplace transform of g if when I Laplace transform such a function, I get g. So we can say that the inverse Laplace transform of g is exponential to the power t times sine of 2t. And that's what we have here. Okay, let's see another example. The inverse, we need to find the inverse Laplace transform of this function g. 1 over s squared plus 2s plus 3. And okay, to get some inspiration from from the first example, we can rewrite this function. And this 3, we can split it in 1 plus 2, which give us this other expression for g, s plus 1 to the square plus 2. And this is quite similar again to alpha over s squared plus alpha squared, but with a shifting. And maybe here alpha is not as explicit as before, but multiplying and dividing by this square root of 2, then we have that 2 can be seen as the square root of 2 to the power 2. So what we have here is this number multiplying, and this is exactly something like alpha over s plus 1 square plus alpha square. So, and we already know that this comes from the sine of alpha t. So that's what we are using here. And again, this is not s squared as the original Laplace transform, but it has a plus 1 that can be seen as a minus minus 1, and then we have a shifting, so we have an exponential. So using these two properties, what we obtain is that we have the sine of square root of 2 times t, this number because it's multiplying, and this exponential to the power minus t because of this shifting, which with minus 1 turns into plus 1. So if we compute this guy, the Laplace transform of 1 over square root of 2 exponential to the power minus t sine of a square root of 2t at s, because of the linearity, we can put out this number, and then we have this expression. Because of the fourth property that we saw, that exponentials goes into shifting, we have the Laplace transform of this other function, the one that is multiplied by the exponential, shift here in minus 1, and that's why there is a plus 1 there. And then we know the Laplace transform of this function, which is this constant over, we have to evaluate in s plus 1, so s plus 1 square plus the constant square, which is equal to 2. And this is exactly our function g. So finally, what we get is the inverse Laplace transform of our function g is equal to the exponential to the power minus t times sine of square root of 2 times t over square root of 2. Okay, so now these two examples that we just saw have in common that both are a constant over divided by a polynomial. Let's see functions a bit more general. They are called rational functions, and this is okay. We have two polynomials, p and q, with real coefficients without common factors. So they don't have roots in common. And let's say that the degree of p is strictly less than the degree of q. Okay, in this situation, we can rewrite this quotient p over q as its partial fraction decomposition. What is this? So for each, we have this q, this polynomial, and we can factorize it. For each factor that q has of this shape, s minus a to the power m, we will add in this expression some terms. We have these constants, a1 over s minus a2 over s minus a squared, a3 with the power 3 here, and so on until we cover all the m's. Okay, so for instance, if m is equal to 2, we only take these two guys. Then for each factor on q that is a quadratic polynomial with complex roots, and we have this power n, what we will add is not just a number here, is a linear function, which is like here is a b1 times s plus c1 over this quadratic function. Then another combination, b2 times s plus c2 over the polynomial to the power 2, so on until we cover the n powers. And we have these constants bn times c times s plus cn. Okay, and all these guys are numbers, okay? Hopefully, I think with an example is a bit clear what is going on, and maybe not in this general setting. But what you maybe have to keep in mind is that each time we have polynomial or divided by polynomial, and the one on the top is has degree strictly less than the one above, then we can rewrite this expression following some rules. So let's just go into the examples. Okay, so first one, this function g, polynomial of degree 1, polynomial of degree 3, so we have that 1 is less than 3, so we are exactly in the situation that I described above. Now, if we factorize this polynomial q, we have this s squared in common, so we have s squared times s minus 1, and we said, okay, this guy s squared, from what I said before, would give us these two terms, a over s plus b over s squared. In the other page, we use the notation a1 and a2, but here it's just better, since we are in a particular example and we know how many constants we will deal with. It's better just to keep a, b, c, d, and not a1 to a2 and so on. So this factor of q will give us these two terms, a over s and b over s squared, with these guys numbers, a and b. And this s minus 1 will give us only this c over s minus 1 term. So what we were trying to say before about this rewriting this function as its partial fraction decomposition is exactly this identity. We will find a, b, and c such that we have this identity. So how do we find these coefficients, these a, b, and c? We know this function, and we work out this expression here, and then we will equate coefficients. So making the computation here in this side of the identity, you have you have to compute these products, and make some computations, and then you find, you gather together the numbers that are multiplying s squared, the numbers that are multiplying s, and the one that are multiplying s to the power 0, so just numbers. And once we have that, we can equate coefficients. So there is no one here with the s squared, which means that this guy should be 0. Then next to s, we have a 2. So that means that b minus a should be 2, should be equal to 2. And there is a minus b here and a 3 here. So that means that minus b should be 3. So that's what we are doing here. Of course, we have the same polynomial here, so we can kill it. And what I just said, this number should be 0, this one should be 2, and this one, sorry, with the minus should be 3. So we solve this little system and we find these values. A is equal to -5, B is equal to -3, and C is equal to 5. You can check if I didn't make any mistake. Okay, now we have our rational function and its partial fraction decomposition here. And what's nice of this? Why do we do this, right? It's a fair question. If we look at this, I have no idea how to compute the inverse Laplace transform of this guy. But if you look at each piece, okay, there are some numbers, right? Like 5, 3, 5. But if you remember the first part of the lecture, we know that the Laplace transform of the function 1 was 1 over s. Then we saw that the Laplace transform of the function t is 1 over s squared. So these guys looks quite familiar in some sense, or well, once you practice a little bit with Laplace transform, they should be familiar. But there is no way that the previous expression doesn't seem to be familiar to any of the Laplace transform that we computed in the first part of the lecture. Okay, so that's the reason why we do this, rewrite this function as its partial fraction decomposition. So that was just rewriting the function. Now the real exercise is, now that you have this expression, why don't you tell me how the inverse Laplace transform of this function? Okay, so the first step was rewriting this function as its partial decomposition, partial fraction decomposition, to make this exercise easy. Then we will use a fact that the inverse Laplace transform is linear. So we want the inverse Laplace transform of this function that we could rewrite as its partial fraction decomposition. And now we use the linearity of this inverse transform. So this -5, -3, 5 go out of the inverse Laplace transform, and then we have to compute these 3 separated guys, which again, I told you they are easy if you remember the first part of the lecture. Okay, so now remember, we have that the first one is the function 1. You can check the first part of the lecture. The second one will be the function t, that I don't know why it's not writing here, maybe it's a bit later on the notes. And this one, if you remember, it was also an example in the first part of the lecture, is the exponential that also shifts a bit here. So if you remember, this is the property. This is what we saw in the first lecture. So putting all this information together, here we have, for this term, now we recall this other property, but for n equal to 1, that we also saw that separated. So it's not super necessary to this property because we also saw the one for n equal to 1. Okay, now putting all the information together, we know that this comes from 1, this one comes from t, and this one from the exponential to the power t. So finally, our inverse Laplace transform of our function g is this 5 exponential to the power t minus 3t minus 5. Okay, and the key here was first to rewrite the function as its partial fraction decomposition. Secondly, using the linearity of the inverse transform, and then properties of the Laplace transform and or well-known Laplace transforms. Okay, second example, 1 over s times s squared plus 1 squared. Okay, so we have two polynomials. This one is degree 0, and this one is degree 2, 4, 5, right? Of course, 0 is less than 5, so we are in that situation. When we factorize q, that is already done here, we have these two factors, s and s squared plus 1 squared. So this guy has only complex roots, so we have to use so this example is different from the previous one. Now we will see. So the first step to compute, we will compute the inverse Laplace transform of this function. So the first step is rewriting this function g as its partial fraction decomposition. I think this s is not okay, then we can correct that in the notes. Okay, so what do we mean with its partial fraction decomposition? This guy s will give us this term a over s with a just a number. And this polynomial will give us these two other terms. Since this is a quadratic polynomial with complex function, instead of just a number here, we will have this linear combination, bs plus c. And since we have a square here, we have this other guy, ds plus e over s squared plus 1 s squared. Okay, so now we work out this side of the identity. Just believe me that here we are just making the computation, and then once we made the computation, that you can check if I didn't do any mistake, we put together all the guys that are multiplying s to the power 4, all the guys that multiply s to the power 3, and so on and so on. And now that we have this expression, we just equate coefficients and get a system. So equating coefficients in this example, we get this system. And solving this system, again, you can check if I did any mistake, if I made any mistake. We get these numbers. A is equal to 1, B is minus 1, C is 0, D is minus 1, and E is 0. Okay, so our function g, which was this rational function, can be written in this nicer way. 1 over s minus s over s squared plus 1 minus s squared plus 1 squared. Okay. Second exercise is, okay, now that you have your function in a nicer way, like written in a nicer way, you will be able to compute the inverse Laplace transform of this function. Other second key, linearity of the inverse Laplace transform. So this minus go out, of the inverse Laplace transform, as you can see here in this step. And then we try to check that these guys are something that we already know. Are they? I mean, we have to check. So this, we already saw that one in the other example. This comes from the function 1. And if you remember what we saw in the second part of the lecture, or the first one, I don't remember. This comes from the cosine of t. And we have this guy that maybe is not so obvious. So we work out a little bit with this one. So remember this property of derivatives and Laplace transform. So if we compute the derivative with respect to s of this function, 1 over s squared plus 1, we get our green function here, but multiplying by this minus 2. So and also we know that this guy is the Laplace transform of the function sine of t. So let's try to put the information together. We know a lot of properties of the function of the Laplace transform, the linearity, how the Laplace transform acts with derivative of functions, this property of the powers of t turn into derivatives, and maybe is this property the one that we are going to use here, and the other that the exponential goes into shifting. So how can we use the property of the powers of t? That is here. So remember that when we have a t, we get one derivative here with a minus. And so in the special case where we have sine here, we get this minus derivative of s of this Laplace transform that we know is this one. And now remember that is coming from this identity. We know we get this function here from the previous computation. So what are we saying is that this is the function that we are interested in. But now, if we apply the inverse Laplace transform here, we get that 2 times the function that we are interested in, the inverse Laplace transform of 2 times the function we are interested in is t times sine of t. Okay, but the Laplace transform and the inverse Laplace transform are linear, so these two can go out first and then go to the other side. So finally, we know that the third piece of our inverse Laplace transform comes from the function t times sine of t over 2. So putting all the 3 pieces together, we finally obtain the inverse Laplace transform of g, which was. So in this identity, we just replace our function g. Oops, sorry. And in the next one, we use the fraction partial decomposition of g and linearity of the inverse Laplace transform. Third step, third identity here, we use well-known Laplace transform in the first 2 terms, and here we have to work a little bit more, and we use the property of powers of t go into derivatives, and that's how we found this inverse Laplace transform of the function g. Okay, and that was it, but remember that all the stuff that we learned today, the definition of the Laplace transform, the properties of these 4 properties, linearity, how the Laplace transform acts in derivatives, powers of t, and exponential functions going into shifting, and finally how to undo the Laplace transform, so the inverse Laplace transform. And this when we have these special functions, rational functions, like a polynomial divided by another polynomial with certain conditions, we can use this partial fraction decomposition to make things easier, and then the linearity of the inverse Laplace transform and well-known Laplace transforms. And that's all what we learned today. And next time we will use all of this stuff to solve ordinary differential equations. Again, the method will be super similar to the Fourier transform method, because we will have these 3 steps of, okay, I have an equation, I transform the equation, then secondly, I solve that easier equation, third step, I go back to get the real solution, because so far I only had the transformed solution. Okay, so we will see this method next time.